Welcome to breadboarding. In this video 14, what we're going to be doing is writing test programs for serial output and serial input tests. So we're going to send data from the nanocomp up to a PC, and then we're going to send data from the PC down to the nanocomp and load into memory. So if you remember in the previous video, we updated our block diagram to include the serial port, also known as a asynchronous communications interface adapter, or a UART. This is driven by a clock, and we've chosen the clock bit rate or baud rate to be 9600 baud, or if we need to, we can speed it up to be 38.4K. This is done by using a divide by 6 chip here. Divide by 3 and divide by 6 is a bit awkward. And this particular clock is designed specifically for doing baud rates. And by using the divide by 12, we can get these sort of lower speeds. If we weren't using divide by 6, then we would be able to get sort of higher speeds like 57.6K and 115.2K are the higher speed. But we don't really need to use those at the moment, especially as given that 9600 baud is able to do about 1 kilobyte in about a second. So we've only got about 4 kilobytes of RAM here, so it's not really a big issue. And this is plugged in to a TTL to USB serial adapter, an FT232RL, which is commonly used for a lot of Arduino type programmers and things. And this just uses the USB port to connect to the PC. And just to go, we've got 2 registers that we'll be accessing the serial port through. There's a control register and a status register, depending on whether we're reading or writing. And then there's the data input and data output register, again, depending on if we read or writing. But there's 2 addresses that we're using here. And it is possible to define interrupts for the serial port to interrupt the computer to attend to these particular events. The transmit data register empty event means that it sent the data, it needs some more. And the receive data register full means it's receiving data and it's got a full byte, and the computer needs to go and read that byte and empty it so it can get the next one. And as we said, there's no need for the RS232 plus or minus 12 volts because we're just using the TTL adapter, and it is accessible on the PC through a virtual COM port or communications port and uses a standard driver. And this is a picture of what we've done. So we've got in the previous video, what we've done is we've got the clock here with the divider. We've got our USB TTL serial adapter here, which we plug in the USB cable in the top here. The yellow wires are wiring it into the various control signals. We've got clock signals coming round to the ports there. And we've also then wired it into the data bus, control bus, and we do have 1 address line that we've copied over from the A0 address line, which has come up from below the board here. So that's the hardware. What we're going to do now is to look at the data sheet, and we'll work out how we need to write the software to send data from the nanocomp up to the PC. And then after that, we'll look at how to send data from the PC down to the nanocomp. Okay, so before we launch into our program, we first need to have a quick look at the data sheet. I'm not going to go through it in great detail, but we do need to pick out a few key things. The serial chip is connected to the data bus with the eClock signal and read-write. There's 1 address signal. The register select, that will determine whether or not we're talking to the input-output send-receive buffer, or if we're talking to the control register and status register. When we're looking at the status register and the control register, depending on whether it's read-write, determines whether we're reading the status or setting the control register. There's a more complex diagram that shows all the various signals that are going on, but in general, to start with, we're only going to look at transmit data, receive data. We won't worry too much about the hardware flow control to start with. We'll just send and receive data, and we won't worry too much about enabling hardware flow control. One of the main things we do need to worry about is after power on, we do have to do the master reset. So we have to set the control register bits 0 and 1 appropriately to make sure that the case here does a proper reset. The chip select is select to Y5, so that's the 5000 range. Talked about register select. We're not going to worry about interrupts at the moment. Clock inputs we're sending in the 3.6 megahertz signal divided by 6, so that's about 614 kilohertz, I think, which will allow us to do, I think, 38K or 9600 baud, depending on the value we put in the control register. The receive data and transmit data, obviously where the data goes in and out, although we need to cross those over when we're sending the data to the USB serial port. There are the transmit data register, the receive data register is where we send and receive the data from. Then the control register, generally referred to CR0 to CR7, are the bits in the control register, and the status register, again, from 0 to 7. And the key things we're going to be looking at there is the receive data register full. The transmit data register empty is going to be the main thing we're looking for when sending data. The errors and things we're not going to do too much with at the moment. So you can see here in the divider select bit CR0 and CR1, we're going to either set to 01 for 16 or 10 for 64, and then 11 is the master reset. We're going to need to do the master reset first, and then we'll like to be using 64, I think, for 9600 baud. We also need to select how many bits and whether or not we want parity. So generally the default for 9600 baud is 8 bits, no parity, 1 stop bit. That's what we'll be selecting there. Then whether or not we enable request to send, I think we'll just set request to send to be low. We're going to have interrupts disabled, so we're not going to confuse things with interrupts, but we will set request to send to be low so that if the receiving end is using hardware control, then things should at least work okay there. Then on the status register, we've got the receive data register full. That means when receiving data, do we need to pick something up from that register? Transmit data register empty means it's sent the data, we need to provide it with some more. Data carrier detect is a modem control signal, and that will always be set to ground, so we don't have to worry about that. In clear to send, we've got configured to connect to the data terminal ready on the USB port. But again, to start with, we won't have flow control, hardware flow control enabled. And then we've got some errors. And then finally, if we want to check the interrupt status, those are the main things we need to worry about. And what I'm going to do now is to show you a very simple program that I've put in. What I have done here is defined the control register at 00, assuming the direct page register of 50, so that means the register is 5000 hex. The status register will be read from, the control register is at 0 and the data input output register is at 5001. So I'm just using the same 0 byte here for control and status, just so we can make it obvious whether or not we're doing things with the control register or the status register, although in fact the values are the same. Then we've got some of the control register bits. So we've got various constants here that we can use, and we can OR these together or add these together to get the right byte value that we want, depending on these things are. So I think we've already said we want to have control divide 64 and 8 bits, no parity, 1 stop bit. It's the other one, and I think we said we were going to have RTS request to send low. So those are some of the things we're going to have. Then these are the status bit values. So the main one being the transmit data register empty, we'll be checking for at some point in time. So that's TDRE, transmit data register empty. So if that is set, then we know that we need to send more data. We'll come across some of these other values later on, but to start with, we'll keep things simple. And finally, we're defining the end of string as just being 00, the 00 byte or a null. We're saying start our code at 1000 hexadecimal. Then we'll initialize the system stack pointer to 1200, so it's reasonably high up in memory. We're going to initialize our direct page register to the 5000 range, which is where the serial port is located, and then we just transfer the A value to the direct page register. Then we're going to load A with the reset bits, which I think is 11 in the bottom 2 bits. Then we're storing that at the serial control register, so that will do master reset. Then we're going to load A with the values we need for divide by 64 8 bits, no parity, 1 stop bit, and request to send low, no interrupts enabled. And then we're storing that at the serial control port again. Then we're going to start reading our message. Now our message is actually down here. So similar to the machine code example I showed a couple of videos ago, what we're doing here is defining some characters, hello world, and then we're delimiting that with the 00 null byte at the end of it. And this is the way how C, for example, delimits strings typically. So all we're doing is making this a string with a 0 at the end of it. And what this loop does is it gets the X index register to point to the message. Each time we load A into A, the next character in the message, we add one onto the index register to go onto the next byte. If we've read the end of string value, so that's the 00, then in fact the 0 flag in the control register will be set, so branch equal will be true. So what that means is once we've read 0, then branch equal is going to say go to serial end. But in fact, all we're doing here is just doing a software interrupt. So that's going to show us the registers that are current at that point in time. And if we continue from that interrupt, what's going to happen? It's just going to go back to the beginning again and run it again. So if we were changing values, so say we changed the serial port configuration on the PC, for example, we could just keep on going around in circles until such time as we wanted to stop this. The key thing we are going to have to do here is we don't have any way of loading software down onto the nanocomp at the moment until we finish this particular video. So what we're going to have to do is just look at the listing of this and type in the bytes manually. There's only about 30 or 40 bytes to type in, so it won't take very long. But once we've completed this work, we'll be able to download programs automatically from PC to the nanocomp. We're also jumping to a subroutine to send character here, and what this subroutine does is saves the current value of A, because that's where the character we want to send is. Then what we do is we load A with the transmit data register empty mask. We then do a bit test, so we read the serial port status and we do a bit test with that port. So basically if it returns 0 or branch equal 0, then it's not ready for data yet. Therefore, we just have to go around. So we go around until the bit is set to 1. When it is set to 1, then we return our saved value from the stack. We store that to the serial data port and we return. So basically what we do is wait until such time as the transmit data register is ready for us to send a value. Then we send it and then we return to the next character. And obviously if that happens very quickly, this will be sat in this loop waiting on the next character we're sending until such time as the serial chip has actually sent all the data. So that's a fairly simple program. What I'm going to do is to start a command prompt. I have got a command prompt here. We'll just make sure we're in the right directory. So if we have a look, just run that, and then we will just have a look at the listing of that file. So serial out, and you can see here this has got all of the output, and it's got the byte values that we need to put in here. So you can see here it goes from 1000 up to 103B. So that's about 60 odd bytes, about that 59, 60 bytes. What we're going to do now then is just to start up the nanocomp, and then we're going to type that in, and then I'll hook up the USB port onto the PC, and I've got a terminal emulator here. So the terminal emulator I use, I think, is called SmartTerm. It's a very simple one, but it does things with serial ports RealTerm, sorry. It's a terminal emulator I use, and this does sending and receiving files and things like that, so quite easily. So that's one of the reasons why I use it. It may not be quite as good as some of the other terminal emulators for real terminal emulation, but as far as messing around with serial ports, then it's quite flexible. Okay, so we've got a nanocomp. So now what we're going to do is just type in the program from the byte values that I've got up in the screen in front of me. So we'll probably go through this quite quickly, and I'll just do any commentary so we can speed it up. Okay, so we've typed in our program. I have gone through and checked it, and I've also now plugged in the USB cable into the serial adapter. What we're just going to do now is to have a look at the PC. So if I share my screen, so here we can see in Device Manager under ports, we've got USB serial port COM5. If we look at this, we can see it's an FTDI USB serial converter. Defaults to 9600 baud, 8 bits, no parity, no flow control. We don't really need to look at the advanced options. It's more to do with the USB side of things. Anyway, when we use a real terminal emulator, this allows us to override all the port settings anyway. There's an interesting program called USB View that's quite handy. This allows you to look at all the details of all your USB devices plugged into your PC. I've got quite a big USB hub here with all sorts of things plugged into it, but the USB serial converter is here, and we can see here there's all the details. So Future Technology Devices International, driver details, all the details about this. You can see it's an FT232R USB UART, so that's what we're expecting. If you ever have any trouble with USB, then this is quite a useful utility to use. So I've run it real term, but at the moment, every time I run this, it's not remembering the port details. So I'm having to select port, COM port 5 virtual COM port, select the 9600 baud, no bits, no parity, 8 bits, and we'll change that and then click open. So we can now see we've got clear to send is showing, so it's picking up a signal on there. So now if I go to my NanoComp and do go 100 and hello world, there we go. So it's not very impressive, but what this means is we're able to send data from the NanoComp to the port here. And obviously if I enabled flow control and send more data, then we should be able to see whether or not flow control of things works. But for now, that's all we need to do. So what I'm going to do now is to see if I can actually receive data from the PC down to the NanoComp. So I'm just going to stop the video now, and I'll switch back to show you the receive program in a few minutes. Right, so now I've got a serial in program. So what this has done is very similar to the previous one we've got. So you've got the same definitions at the top here. They are the same. The only thing that's different is that this program I've got running at 1200. The only issue I need to do is just to change the stack there, otherwise you might overwrite things. So the origin here is at 1200, whereas the previous one is at 100. And the reason for this is what I'm going to attempt to do is by saying our code start is at 1000 and the code length is 3B. If we go back to our original, the previous program we've done, what we'll find that it starts at 1000 and it ends at 3B. So it's 3B long, or it has a zero at the end there. So what we'll try and do is we will send the binary file produced from this assembly. So if we look at the serial out bin, and we look at that in the text editor, so we can see here that we've got about 3D ends with null byte there, 00. So we're going to try and send that and see whether or not we get an executable program in the starting point of 100. Now I have reset the NanoComp, so at the moment in the memory 100 there is just random data. We don't have the original program in there, so it is a valid test. What we're going to do here, what this does then is initializes the system stack. Again, loads the direct page register of 50, so we're working with 5000 for the serial port. We do the reset, we store that in the serial control port. We then load the divide by 64, 8 bits, no parity, 1 stop bit, set request to send low, and we store that to the control port. Then what we're doing is we're in X, we're going to have the code starts. This is starting at 1000. We've got B is the length of the code. So then what we're doing is receiving the character. So what the receive character does is masks the received data register full bit. So A is stored with the mask bit for that. We then do a bit test on the serial port status, and if that is 0, then we haven't got any data. We're still waiting for data. When that does return 0, then we know we've got data, so we then load A with the serial data, and then we return. And then what this will do is it receives the character, or receives the byte, I should say. So these aren't characters really, these are just bytes. These are raw bytes, they're not ASCII characters or anything like that. So we'll just store the raw character text, increment X, decrement B, and we keep on going until such time as we get to 0. So what we should find is if we were to then go to the memory 100, what we'd expect to find would be 10 CE 1200, and then down the end, if we went to 102E, we'd expect to see our hello world message, and 103B, we should get 00. So one of the things we might have a problem with, if we don't get our looping quite right, we might miss out on the last byte or something. But let's see whether or not this is in fact the case. And what we're going to use when we're in the terminal program, what we can do is to send a file. So we could actually choose the file to send. We're actually going to be sending the serial out. So it'll only send it when I hit send file. So you can see we've still got the data left over from the test here. So we're lined up here to send that binary file when everything's set up. So what we're going to do now is just go back to our source code here. Again, we're going to have to type this in. So what we're going to do is just take the first command. You'll see I've got 2 commands here. One is produces the binary file, and the next one uses an SREC, the Motorola text file format, and that's what we'll be using for our send and receive when we update the monitor to do that. But to start with, just testing out the serial port, let's just do this command. And just showing at 1000 where we're going to be losing at the moment, there's just random data, there's nothing meaningful there. So what we need to do now is we'll run up the program. It should just sit there waiting for some data to be received. So I'm just going to run it here, and then we'll go to realterm to actually start sending data. So we need to actually run the procode at 1200. It's just sitting there waiting there now. So let's go back to screen, and so we're in SmartTerm here, and if we now go and send this file, hopefully what we should see is some activity. Okay, and it has in fact finished. When I go back to, we've actually got the software interrupt there. So if we just go to memory 1000, we have 10 CE 120. So that looks like we've got everything. And if we go all the way down to the bottom, we should find that at around 2E, I think it was. Four 86560. So this is the message. And then at the end of the message, we should have the 0 at the end. So the only issue we may have here is we may not be getting the 0 at the end because it's used. We might have to increase the length of our message slightly, but let me just check the serial out. So yes, we have 3B should be 00. So if we just go to memory 1030, 6C, 6C, 6F, 2C, 2077, 72, 64, 21, then the next value we should have is 00 at 3B. So you don't have that. So in fact, the only issue here is that we've got this sort of classic, do we count zeros and things like that? So in fact, what we probably needed to do is the length of our code is not in fact 3B, because we have to count 0 as well, so it's actually 3C. So in fact, what we should have done for our serial in, we should have said the length of our code was in fact 3C. We go back to serial in. So because we hadn't counted 1000, we were counting 3C, 3B, but we needed to add 1 onto that. So it's your classic not counting 0. But that should load the 0 in there anyway. So the only thing we need to do then is to, if I go to memory 103B and put in 00, and what we should be able to do is go back to our terminal emulator here. If we clear the screen, and I'm just going to go into here and say go 1000, and we got hello world. So what this is proven is that we've been able to download the send program from the PC to the memory of the Nanocomp, and then we've been able to run it. The only issue we had is that the terminator, the 0, wasn't there. And in fact, what happens, if I just show you what happens if we go in and change 103B, we change the 00 to something else like 65, and then we run the program again, what will happen is it will carry on sending junk until it comes across a 0. So if I run 00 again, what you can see there is it started to send junk until such times it comes across a 0 in memory. So that's what we would expect to happen if the 0 end of string has not been found. So what we've got there then is a working serial port. The inbound and outbound's all working nicely. So we've now written our test programs and shown that the serial port is able to send data from the Nanocomp to the PC, and we can also send data from the PC down to the Nanocomp. So in the next video, what we'll be doing is enhancing the monitor ROM to be able to send and receive data from the PC using the Motorola SREC format. SREC or S19 is a data format developed by Motorola for sending data from a computer down to a microcontroller or a smaller computer, or for burning into ROM. It's quite a simple, straightforward format. What this does mean, though, is that on the assembler, we can output the program in SREC format, and that allows us to download the output from the assembler directly down to the Nanocomp and run it. It makes things a lot simpler for developing software. I hope you found it interesting. If you don't want to miss out on future videos, please hit subscribe, and if you found it useful, please hit like. It just helps to put the videos a little bit higher up the list so more people can get to see them. Thanks for watching.